Assalamu alaikum everyone. This is Fahd Ansari and I'm here to help you conquer chemistry. In this video, we will be talking about metal. No, not this metal. Really sorry about that. What I meant was this metal. The metallic elements and the bonding within them, right? So we already discussed one type of bonding, which was ionic bonding in the previous video. If you don't know what I'm talking about, you should watch that before you get on to metallic bonding. So in metallic bonding, basically this is the type of bonding that occurs within metallic elements, right? So let's take the example of a metal. Let's say we have copper, right? Chemical symbol Cu, right? Now, what happens in a sample of copper is that you have a giant ionic lattice. Now, does this term seem familiar to you guys? If it doesn't, again, you should watch the previous video on ionic bonding. So there's a giant ionic lattice within a sample of copper. Now, we know that copper is a metal, so it will form positive ions, right? So we have a giant ionic lattice of positive ions or cations. Now, copper tends to form 2+ ions. Basically, you have copper atoms that lose 2 electrons each. That gives you a copper ion with a 2+ charge. So I'm going to draw a few ions over here of copper. And you might be wondering that these are all ions with the same positive charge. Now, wouldn't they repel each other? Normally, like charges tend to repel, but these guys are somehow, sitting comfortably, relaxed, all chill, not really repelling each other and creating a mess. Why is that? The reason is that the repulsion between these positive ions is basically all but cancelled out and then some by the attraction between these positive ions or cations, call these cations, and the attraction is between these cations and the electrons that they have lost, right? Cations are formed by the loss of electrons, so you have 2 electrons that are formed by that are basically lost to form a 2+ ion, right? So 2 electrons are lost in order to form a 2+ ion. So each 2+ ion has been formed by the loss of 2 electrons each, right? And it is the attraction between the cation or the positive ion and these negatively charged electrons. This force of attraction is, ladies and gentlemen, your metallic bond. And this attraction is so strong between these oppositely charged species, the positive ion and the electron, that the repulsion between the cations in the giant ionic lattice is basically overcome, and that there is still some attraction left over to form strong metallic bonds. That's why metals tend to be very strong, generally speaking, right? So to sum this up, metallic bonding occurs within metallic elements, right? And we have a giant lattice of cations or positive ions, as you can see over here. And these are surrounded by a sea of delocalized electrons. So you can imagine the lattice of cations is a ship, and it is floating in a sea of these delocalized electrons. Now, what does this word delocalized means? This delocalized term basically means that the electrons do not belong to any one atom anymore. They're free to move between the cations in the lattice, right? And because of these delocalized electrons, we have quite a lot of properties, right? These electrons are delocalized or mobile or free to move, not restricted to one atom. So, properties of metals include high melting points because of the strong metallic bonds between the cations and the delocalized electrons, right? So strong metallic bonds that require a lot of energy to break, that gives you a high melting point. So these are good conductors of heat as well as electricity. This is true for all states, whether it is solid, liquid, gas, right? Well, first of all, it's very difficult to convert a metal into a gas, if at all possible. But still, solid and liquid metals can conduct heat and electricity, and it's thanks to these fellows over here, these delocalized electrons, right? These delocalized electrons that are free to move from one end to the other. So if I apply some heat over here, the electrons, they gain kinetic energy, and they can move faster from this end to the other end. They move in this direction from the hot end to the cold end. And similar thing happens if you apply a potential difference across the strip of metal, right? So electrons are free to move, so they can conduct heat as well as electricity. That's a useful property of metals. And metals are also malleable and ductile. Now this has nothing to do with the delocalized electrons. This has more to do with the fact that you have a giant lattice of cations in a regular repeating pattern of positive ions. They're all of the same size, right? So you can see these are uniform layers of same-sized cations. And because of this, if I were to apply a strong or large enough force on one layer, it could easily slide over the other layer. So let's say I apply force on this layer, it can easily slide in this direction over the layer over here at the bottom, right? And over this layer at the top as well. It could slide in between them if you apply a strong enough force. But malleable basically means that you can apply strong enough force to shift these layers that are uniform, but without the metal breaking, and that has to do with these strong metallic bonds that are present, right? Yes, the layers will shift, but because the electrons are moving as well, so the bonds move along with the layers. Ductile basically means that you can apply strong enough forces to twist these metals into wires, right? So both of these properties basically come from the fact that you have uniform layers that can slide over each other with strong enough forces applied. So alloys are different from metals. These are mixtures. These are not pure elements or compounds. These are mixtures. These contain at least one metal. For example, you have steel, right? Now steel contains iron and carbon and chromium. Now in this mixture you have iron and chromium that are metals, and you have carbon that is a non-metal. So these two guys are metals. This fellow over here is a non-metal. So at least one metal is necessary to form an alloy. Normally you melt these metals and mix them in the liquid state and then allow to solidify it to get an alloy. Now alloys are formed because they are stronger than pure metals. Now why is that? Because you don't have layers of same-sized cations anymore. What you do have are layers that involve ions that are of different sizes, right? So if I have ions of different sizes, right? These are all cations, by the way, all carrying positive charge. So because you have ions of different sizes, that if I were to apply a force on this layer, it's going to get stuck, right? Because these ions are of different sizes, this layer is not going to be able to slide easily. It's going to face some resistance because of all the ions from different layers, right? And that's what makes an alloy stronger than a pure metal that tends to be normally soft. That's why you don't use pure iron in construction. You use steel because it is much stronger, right? And these alloys are also more resistant to corrosion. Now, not going to go to the details of what corrosion is, but just imagine that I'm talking about rusting, right? It's one form of corrosion, right? Iron can easily rust if it's left out in the air and it's in contact with water, but if you add to it carbon and chromium, then you get an alloy called steel that protects the iron from being corroded or ruined, right? So that's why we form alloys. Alright, so this was all about metals and metallic bonding and all the properties. If you like this video, don't forget to like and share and do subscribe to the channel. Inshallah, I will see you in the next video.